quickly, and then I want to divert into my shtick, because I don't think this chapter does a good job at all of hitting the significant high points of what it needs to hit. The first problem I have with this chapter is the title, Resonant Circuits. Resonance only occurs at a unique set of circumstances are met, period. So in essence, this is about RCL circuits. Below resonant frequency, RCL circuits above resonant frequency, and RCL circuits at resonance. If this was just about resonance, this lecture would be over already, okay? Because at resonance, X sub L cancels out X sub C, and there's only R. And do all of you know how to add up R in series, R in parallel? Can you deal with R? Do you know everything there is to know about R? Then that's the end of the lecture, if this was about resonance, period. Okay, it's a little bit more than resonance. So we'll spend a little bit of time with this here. After completing this chapter, you're going to be able to identify the formulas for determining capacitive and inductive reactance, identify how AC current and voltage react in capacitors and inductors, determine the reactance of a series circuit, and identify whether it's capacitive or inductive. Define the term impedance, solve problems for impedance that contain both resistance and capacitance or inductance, discuss how Ohm's law must be modified prior to using it in AC circuits, solve for X sub C, X sub L. We're not going to solve for S because I don't even know what the heck that is. Siemens, I don't know, Z and IT and RCL series circuits, and solve for IC, IL, IX, IR, IZ, and RCL parallel circuits. Okay. Reactance in series circuits. When an AC voltage source is applied, the instantaneous value of current flowing through the resistor varies with the alternating output voltage applied. Ohm's law applies. Peak current is calculated from source peak voltage. RMS current is calculated from RMS voltage, meaning we can't compare apples and oranges. If we're dealing with a peak value, peak voltage, we deal with peak current. If we're dealing with RMS voltage, we deal with RMS current. Okay? So first slide, any heartache? Makes sense, right? Hopefully nobody's got heartache with this. Two simple series circuits. On the left we got a DC circuit. Okay, direct current flows negative to positive. I got counterclockwise current flow through this circuit, through R1. AC, resistor. AC is alternating current, so this current's going back and forth, back and forth all day long, because that's what AC does. The math associated with this, if this was 10 volts in a 1K resistor, and this is 10 volts RMS in a 1K resistor, exact same amount of current for both circuits. They're both going to behave identical. Make sense? Okay. When a circuit contains pure resistance and no reactive components, both voltage and current are in phase. Remember that chapter? AC, resistive circuits? I made fun of that chapter too. Now, the effects of pure inductance or capacitance cause the voltage and current to be 90 degrees out of phase. Well, the best thing in dealing with this is remembering the phrase that pays, which is
ELEC.
Eli the ice dude. Okay? In an inductive circuit, voltage leads current by 90 degrees. In a capacitive circuit, current leads voltage by 90 degrees. Make sense? An AC circuit typically combines both reactive and resistive components. Voltage and current are in phase in the resistive portion of the circuit. Why? It's pure resistance. They're going to be in phase in the pure resistance portion of the circuit. Voltage leads current by 90 degrees in the inductive portion of the circuit. voltage leads current by 90 degrees in the inductive portion of the circuit. Why? That was last chapter. Make sense? That's where it gets fun. That's where it gets fun. We'll take it easy though. We use vectors. We use vectors. Everybody put down your pens. Don't take notes on this because this is going to be a dirty word. We're going to use trigonometry. As soon as I say trigonometry, a lot of people get their freak on. Oh, I don't want to do that math, and I can't do that, and I sucked at trigonometry in school. You know what? When I was in school, I sucked at trigonometry too. But you know what? Now I do it. And now I could look at this in my head and almost do it. And I'm not bragging. It's just that I see the direct application for trigonometry with AC. When I was in school and they were teaching me this stuff, you know, calculating out the height of a church steeple, I'm like, I am never going to do that. Why would I be out trying to calculate out the height of a freaking church steeple? I mean, that is stupid. I'm not going to do that. You know, for math, for electronics, this makes sense. So we're going to use vectors used to show the relationship between voltages in a reactive circuit. Now the type of circuit that we're looking at here, just by me seeing this vector diagram, I know what kind of circuit we're looking at. Do you know what kind of circuit that we're looking at here? We're looking at a circuit that contains a resistor, and we're looking at a circuit that contains a inductor. This is the voltage across the inductor, and this is the voltage across the resistor. What kind of a circuit are we looking at? What kind of a circuit is going to have two voltage drops? Series circuit, because a series circuit is also known as voltage divider. So just by looking at this, I could tell what kind of circuit that we're looking at. Okay? If you can't, you may want to draw the circuit, right? So this is going to be an AC series RL circuit. Does that make sense? AC, we're going to have two pieces here. One is going to be the voltage, the other is going to be the frequency. In a series RC circuit, we're going to have resistance, which is going to be measured in ohms. And we're going to have inductive reactance, which is going to be measured in ohms. To calculate out this value, I'm going to need to use the formula X sub L equals 2 pi FL. I get the value of F from here. I get the value of L from whatever L equals on my schematic diagram or bill of materials or wherever I'm getting my most accurate data from. Does that make sense? So this is the circuit that we're dealing with. If to analyze this circuit, we have to use these vector diagrams. Now, some of the stuff in this book I kind of dig, some of the stuff I don't dig. One of the things I don't dig is this illustration right here, because this is not accurate. And if you're going to do trigonometry, we probably want to do it right so we could recognize what's really going on. This is not to scale. This is not to scale. They're showing this here. Let's round up. This line, this vector right here, they're showing it at a magnitude of approximately 90 volts. 89.5, 90 volts. Make sense? This vector here, they're showing at a magnitude of approximately 45 volts. Now, when I was in school, 45 is half of 90. Does this look like this is to scale? Okay, so what I'm going to do here, everybody got this, what the circuit looks like? Everybody know it's a series circuit that we're dealing with here? Let me erase this. When you're doing this, when you're doing these problems, I highly recommend you use a straight edge, a ruler. Where the heck is that? That thing was around. Did somebody abscond with that? We had that engineer's rule. Is that around?
Small straight edge, made it.
Did that work out okay? Cool. Gracias. Thanks. Somebody needed it more than we needed it. I got a yardstick here, but I'm talking about the engineering rule that was up here.
Yeah, I don't know.
Somebody up's kind of. Everybody know what I'm talking about with an engineering rule? It just has different graduations on it, and they use it for drawing. You could use a yardstick, you could use a ruler, you could use, as long as it has specific gradients marked. So what I'm going to do here is I'm going to draw this again accurately, so you see what we're doing. ER is going to be 90 volts. So what I'm going to do for the case of illustration here is, since EL is 1/2 of ER, what I'm going to do here is I am going to make ER 24 inches. I'm going to make it 24 inches. So this is going to be my reference point. And then I'm going to draw this. And I'm going to label that ER equals, we might as well use the right number, 80, well, no, let me use my numbers. 90 volts. Everybody see that? So now I'm going to draw EL. EL. And what does voltage do in an inductive circuit? It leads current, okay? So what we have to do is show a 90-degree phase difference of the voltage of the resistor and the voltage of the inductor. Because there is a 90 degrees phase difference between the two. Remember that 90 degrees difference? ER was 24 inches to represent 90 volts. So EL is going to be how many inches to represent half of that? 12 inches. So I'm going to go ahead and draw this. 12 inches. At 90 degrees, exactly. This angle here has to be 90 degrees, because in our resistive portion of the of our vector here, how much phase shift is there through the resistor? How much phase shift does a resistor have? It's not a trick question. Zero. 0 degrees of phase shift through the resistor. How much phase shift is there through the inductor? 90. So this is what I'm drawing right here. Make sense? Okay. So this is going to be, what do I label this? L. And this is going to be equal to 45. We're rounding off just to make this easy. Okay. So now I've got my two sides of a right triangle. I have my two sides of the right triangle. Any trig experts here? Does anybody know what we call these different sides?
Adjacent and opposite.
Okay, which is which? Who's on first?
Depends on which angle you're figuring out. But,
From the
No, you're BSing me. Well, it depends on which angle you're figuring out, which day of the week it is, and come on, man.
Would be the EL.
This would be the.
Opposite would be the ER.
I got it backwards. Okay, this is going to be our reference. This is going to be our adjacent side. This is our adjacent side. So this is going to be our reference. This here is going to be what we call our opposite side. Okay. And then does anybody know what we call the combined adjacent, opposite, and the hypotenuse? And mathematically, what we're really doing is this opposite side. We call it the opposite side because we're going to move it to the opposite side, literally, mathematically, over here. And then what I'm going to do is I'm actually going to draw a line from my reference to complete this right triangle. And this line that I'm drawing here, oh, come on, man. This line that I'm drawing here is going to be my hypotenuse. And the combination of the voltage across my resistor and the voltage across my inductor is going to be my voltage total, or my hypotenuse. Does that make sense? So do you see, how does my drawing differ from their illustration? It's in proportion, thank you. Whose is in proportion? Theirs or mine?
Yours.
All right.
You took
That's the right answer.
2 foot, 1 foot.
That's the right answer, okay? The big thing though, the big thing is this angle right here between my adjacent side and my hypotenuse. This is a critical angle. We call this theta. We call this theta. And this shows me how much overall phase shift there is inside this entire circuit. How much phase shift is there in the resistive portion of the circuit? 0. How much is there in the inductive portion? 90. How much is there overall? How much is there overall? Who's good with angles and dangles? Give me a guess on this. What do you think this is? How much? 35 degrees? What was that, 35 you said? Question, 35 degrees. What's another one? 45? Why is 45 a bad answer? I don't want to pick on you, but you threw 45 out there.
If both sides were equidistant, it would be 45.
If this was 90 and this was 90, it would be 45. So ultimately, just to play it safe, what's the answer going to be here? It's going to be less than 45 degrees. You agree with that? And for those of you that made the wild guess, 35, 33.8 degrees, whatever, you're on the right track. That's one of the reasons that I want you to draw it like this on a piece of scratch paper. Because when you see it, I could look at this angle and I say, this is less than 45 degrees. That's actually around 33 degrees, 35 degrees. Okay, that tells me that this is predominantly a what kind of a circuit? Resistive circuit. But I do have some reactive elements to it. But it is more resistive than it is reactive. Why? I'm looking at it. I got 90 volts voltage drop across my resistor. I got 45 volts across my inductor. I got half of this. Half my voltage is across the inductor. Now, what is the total voltage in this circuit? Give me a guess on what the total voltage is in this circuit. VT. A guess. Put the calculators away. You can do the calculators, use calculators on your homework and on the quiz. I want you all to think in here. 100 volts. 100 volts? You think this is 100 volts? If this is 90 volts, how did that get to be 25 inches? It was 24. There it is. If this was 90 volts, this mark right here would be 90 volts. So going out to this point here, approximately 100 volts. Do you agree with that? Does that make sense? Freaking hilarious. It's freaking hilarious. On professional examinations, they will say in a series AC circuit that contains a resistor and an inductor, you have 10 volts voltage drop across your resistor. You have 10 volts voltage drop across your inductor. What is total voltage? Answer A will be 20. And you'd be surprised the number of people filling it in. Answer A. Because 10 plus 10 is 20. And a series circuit is what? Series circuit is what? It's a voltage divider, right? The answer is not 10 plus 10 does not equal 20 in a series AC circuit. 10 plus 10 is going to be what? It's going to be something more than 10, but it's going to be something less than 20. And I guarantee you on a multiple choice test, only one answer will be correct. So don't get suckered in that one. So does this make sense? Now, I'm not going to have you just guess at this stuff. I'm going to have you use a scientific method. I'm going to have you use a proven method called the Pythagorean theorem. The Pythagorean theorem. Does anybody know the original Pythagorean theorem? Like
A squared plus B squared equals C squared.
A squared plus B squared is equal to Huey Lewis, right? It's hip to be square, right? In the 1970s, he had hair down to his butt. In the 1980s, all of a sudden, it's hip to be square. This is the Pythagorean theorem. Now, we know that what we could actually do is replace these values with electrical values. And that's what we're going to do. And in using algebra and reorganizing this formula, what we're going to do is calculate out voltage total is going to be equal to the square root of the voltage of the resistor squared plus the voltage of the inductor squared. Does anybody know what we call this? When I want to add up these two voltages, what do we call it? We call it the vectoral sum. The vectoral sum. So total voltage in this circuit will be the vectoral sum. So why don't you go ahead in your calculator, use my numbers. Don't use their numbers on the board, use my numbers. What do you come up with?
180.
180?
No, I...
100.62 volts.
100.62 volts. Peak, RMS?
Considered to be RMS.
Peak to peak? Yeah.
Unless otherwise specified.
Thank you. And if it's not RMS, convert it into RMS and then perform the math. Because you should always be dealing with RMS when you're dealing with this. Make sense? Everybody get that number? This 90 volts is occurring at a different moment in time than this 45 volts. So if we, with asking for VT, we're looking at what's the cumulative overall effect in the circuit. Does that make sense? Okay. We could also do impedance this way. And in doing impedance through this method, it's going to be the same thing. Well, if we're getting a bigger voltage drop across the resistor than we are across the inductor, what does that tell us right off the bat? Not necessarily a high-pass filter, but if we're getting a bigger voltage drop here, there's more ohms of resistance than there are ohms of reactance. And as a matter of fact, the exact same vectoral plot is going to work. The exact same. So what you're literally looking at right here is R. Here you're looking at, if I'm looking at R on my adjacent side, what am I looking at on my opposite side? I'm going to compare R to X what? XL. XL. Very good. And what's the combination of resistance and reactance inside a circuit? Z. So if you want the formula for Z, Z, T, if you like, is going to be equal to the square root of R squared plus X sub L squared. If you don't have the value of X sub L, you need to get it. And execute this formula. But the vectors are going to be exactly the same. Exactly the same. They have to be exactly the same. Because resistance is what creates a voltage drop. Reactance is what causes a voltage drop. So you're going to plot this out exactly the same. What's something else that we could plot out this way? What else is additive in a series circuit? What else is additive in a series circuit?
Power.
Power. Isn't power additive in a series circuit? That's actually a safe answer because power is also additive in a parallel circuit. So I could do the power of my resistor here, because obviously the bigger resistor, the bigger voltage drop, it's going to dissipate more power. I could do the power of my resistor, and here I could do the power of what? Power of my inductor. And then here, this would be what? My power total? What's the problem with what I just put up on the board? There's a problem. Thank you. So this is what we would call the apparent power. Apparent to who? Apparent to one of Joe Grenick's students that dropped out of this program and thought they knew everything about electronics and went on with their life. Because power is additive. I have power across the resistor, I have power across the inductor, that's going to equal power total, right? No. This will equal apparent power. Inductors really don't dissipate energy in the form of heat. So actually I could do that same Pythagorean theorem though. This would be power total, APP, apparent power total, is going to be equal to square root of power of the power of the resistor squared plus power of the inductor squared. There's another thing that we deal with these types of circuit. It's called true power. You know what true power is equal to? The true amount of power being consumed in the circuit. How much is the true amount of power being consumed in the circuit? The power being consumed by the resistor. So a true power is going to equal this vector, period. There is going to be no power total. Power total is going to be PR. That's going to be true power in the circuit. But mathematically, the same vectors would work. It's just apparent power is kind of irrelevant. It's not the truth. That's why we have true power. True power gives us the truth. Does that make sense? The only other thing that you could work with here is, or the only other thing that you need to solve, be able to solve for this in a series circuit, is angle theta. Angle theta. And if you know any two sides of the right triangle, you could solve for angle theta. And one of the phrase that pays, the one that I always remember, it's silly, don't laugh, got me this far in life, right? Some old horse came hopping through our alley. Some old horse came a-hopping through our alley. Sine function, opposite over hypotenuse. Cosine function, adjacent over hypotenuse. Tangent, opposite over adjacent. So let's go back to the original numbers that we had here. I had the opposite and I had the adjacent. Opposite and adjacent. So why don't you go opposite 45 divided by 90? 0.5? And what's the tangent of 0.5? Or inverse tangent, put that into degrees. That's tangent with a little -1 up above it, inverse tangent. Key on your calculator. $26.6. Does anyone else concur? Who else got that? Mark, did you get that?
26.5.
26.5? Got to make sure your calculator's in the degree mode on these. If your calculator's not in the degree mode, if it's in radians or gradients, you're going to get goofy numbers. So all you have to do is take this opposite, divide it by adjacent, 45 divided by 90, then take the inverse tangent of it. That's tangent. Typically in your calculator, it's second function, tangent -1. Everybody get that? Everett, did you get that? I could tell, man, I got the best seat in the house up here, man. I see dudes like, all of a sudden, like getting shifty, squirming in their seats and stuff.
It's just that this calculator does things differently.
Divided by 90. 45 over 90. Yeah, look at that, 26.56. So we were all wrong. Well, no, I was right. I said it was less than 45. We had a 35. That was in the ballpark. That was in the ballpark. Definitely not 45, and we knew it was less than 45, so 26.62 Degrees. I said percent here. Degrees. Degrees. That's how many degrees we are. So if you told me, there's so much, by this illustration, there's so much that I could tell. By just looking at this, I could tell this is a series RL circuit. I could tell that this is predominantly a resistive circuit, but it has some reactive components. By me seeing that it's 26.6 degrees angle theta, that tells me that it's predominantly resistive and it's not reactive. If I wanted to make this more reactive, if I wanted to increase the length of my opposite side, how can I do it? How could I do it?
Make it longer with your pen.
Make it longer with my pen. He gets an A for the day. You fail the quarter, but you get an A for the day. If I want to make this line longer, and by making this line longer, what effect is that going to have on angle theta? It's going to increase angle theta. How could I do this? How can I make my opposite side longer?
You want more reactance across voltage. You would bring your frequency down.
If I lower my frequency, I lower my X sub L. If I lower my X sub If I increase my frequency, so for the same inductor, I increase my frequency. If I increase my frequency, I increase my X sub L. If I increase my X sub L, my opposite side gets longer. My voltage drop across the inductor gets longer. My power across the inductor increases. Angle theta increases. You see how many questions I could ask you from just this problem alone? I mean, it's mind-boggling. It's a big chapter. This is the biggest chapter. Really is, because everything comes together. If you don't believe that series circuits power and a voltage is additive, then we got problems, you know. But if you buy, does everybody buy everything that I've sold them up to this point? Is this beyond your comprehension? Or is this right in the zone for what you've been studying? Kind of makes sense, doesn't it? What else can I do with this circuit? Really nothing. What's current in this circuit? First of all, what kind of circuit is this? What's the most important thing about a series circuit? Current's constant. So what is current going to be for this circuit? How would we calculate out current in this circuit? How would I calculate out total current for the circuit? IT equals E over R. In an AC series circuit like this, do I have R anymore? Bzz, close.
You have R and XL.
And what do we call the combination of that?
Z. Well, you need to find XL first.
Absolutely, that goes without saying. But this formula IT is going to work as long as it's ET over ZT. How do I calculate out ZT? With this formula right here. How do I calculate out this formula here, R and X sub L? I got to calculate out X sub L. 2 pi FL equals X sub L. Once I have X sub L, I plug it into this formula. The vectorial sum of R plus X sub L. Once I have that, then I could solve for IT. IT is equal to E over ZT. And where would I plot that out on this here, on my vectorial plot? Where would I get plotted? Down the bottom? Where? On the same vector as what?
Resistance.
Absolutely. Why?
Because resistance is in phase with current.
And total current is total current. Whatever's happening at one point is happening at the other point. There's no phase shift of current in the circuit. I mean, from any point in a series circuit. So this is also going to be IT is going to get plotted out on this vector. IT. Does that make sense? There's a lot going on here. A lot going on here. So, to calculate out any vector, use the Pythagorean theorem, which states E is equal to the square root of ER squared plus EL squared. We call this the vectorial sum. The vectorial sum can be used when two legs are known. Vector representation allows the use of trigonometric functions to determine voltage when only one voltage and phase angle is known. The two voltages are known. Sine theta is equal to voltage of the inductor over voltage total. Cosine theta, ER over ET. Tangent theta, EL over ER. I remembered that over here by sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. If you can't remember that, remember some old horse came a-hopping through our alley. Get that on your scrap paper, because I'll tell you what, when I start hitting you on a quiz with these questions, you're going to forget this stuff. I give you any two of those sides, you're going to be able to calculate out what angle theta is. If angle theta is greater than 45 degrees, it's going to show you that it's predominantly a reactive circuit. If it's less than 45 degrees, it's predominantly a resistive circuit. If it's 0 degrees, it's purely resistive. If it's 90 degrees, it's purely reactive. If it's 45 degrees, it's perfect. Half resistive, half reactive. Make sense? Impedance, the combined effect of resistance and reactance, must be used to calculate out current in a reactive circuit when the supply voltage is known, represented by the capital letter Z. Reactance in parallel circuits. Parallel circuits. Parallel circuits containing inductors and capacitors may be analyzed with vector diagrams. What kind of vector diagrams are we going to want to use in parallel circuits? A parallel circuit is also known as what? Current divider. So what kind of vectors are we going to have to use? Current. Can I use voltage vectors in a parallel circuit? Why not? Voltage is constant. Very good. There is no phase shift of voltage in a parallel circuit. What the voltage is the voltage. Do I need to draw a parallel circuit on the board, or do you remember what it looks like? The tops of all the components are holding hands, the bottoms of all the components are holding hands. So whatever voltage is compared to the top and the bottom, that is a constant value, period, end of story. Make sense? So in a parallel circuit, we have to use vector diagrams. Voltage across each component must be equal and in phase. Must be. Whose law is that? Kirchhoff's law, parallel circuit. Voltage is constant across a parallel leg. See, I don't have to draw it. It's already been drawn for me. Here's our parallel circuit. Voltage across the resistor is the exact same voltage across the inductor. The current through the resistor, what angle is this? What side of the right triangle is this? Adjacent. Which side is my inductor, current through the inductor? Opposite. My hypotenuse is going to be the total current through the circuit. The combination of this and this. Classic example on a professional exam. You take your CET exam or your FCC exam, they'll give you this circuit here and say you've got 2 amps flowing through your resistor and 2 amps flowing through your inductor. What's total circuit current? Answer A will be 4 amps. Answer A is wrong. You know it's going to be more than 2, but less than 4 because it's the vectorial sum that you're actually calculating out. Does that make sense? In a parallel circuit, the book shows you this technique here. The reciprocal of reactance, the reciprocal of resistance equals the reciprocal of impedance. My recommendation is you don't do this. My recommendation is you don't use this formula because the reciprocal of inductance and the X sub L, the reciprocal of, there's a lot of moving parts to this. You're probably going to slip a finger in a calculator and get a wrong answer. If that's the case, how can you calculate out impedance in a parallel circuit? How can I calculate out impedance in a parallel circuit? How did I calculate out resistance in a simple DC circuit? R is equal to what? Ohm's law.
Current times. Voltage over current.
Again, if you mess yourself up, right? E-I-R-R, E over I, E over I. Does that make sense? So if I'm dealing with an AC circuit, impedance is going to be equal to what? E over I. The good news is this should be an easy one to get because it's the same voltage across the parallel network. This is kind of engraved in stone in a parallel circuit. How am I going to get this number?
You have to find reactance.
IT. No, you don't have to find out reactance. That's the whole thing. I don't recommend you do that. You can find out reactance.
This is where I went sideways.
Good question, right? If this is, what has this got, an inductor in it? X sub L equals 2 pi FL. You just calculated out your reactance. End of story. If you want to calculate out your total current in the circuit, square root of current through the resistor squared plus current through the inductor squared. How do you calculate out current through the inductor? How do you calculate out current through the inductor? How do you calculate out current through a resistor? R is equal to, or I is equal to E over R. So I is going to be equal to EL over what? XL. That gives you this number. Once you have this number, you plug it into this formula. Once you get this, you get this. Once you get this, you can plug it in here and get this. It's a heck of a lot easier than the reciprocal of the reactance. And I mean, how would you, this would be like, help me out with this one, guys. This is,
So then is
1 over...
IT is the vectorial. Is the...
Absolutely. Vectorial sum.
Right.
Has to be. Has to be for this kind of circuit. So this would be like IZ is equal to the square root of 1 over R squared plus 1 over X sub L squared. Don't. Don't. It's a lot of keys you got to hit for a simple question. Okay? You want to calculate out your total impedance. Z is equal to E over I. I, you get from IT. I is the vectorial sum of current through the resistor, current through the inductor. You calculate out current through the inductor by calculating out voltage of the inductor over inductive reactance. A lot easier. So don't do what the book tells you to do. If you want to play with this and just see if you can do it, and hey, look, Mom, look what I did. No hands. You know, cool, do it. But beyond that, I'd stay clear of that formula. Actually, there's a cool formula. Want me to show you a cool formula? Or you guys had enough cool formulas? Want to see a cool formula? Remember when I had two resistors in parallel with each other? Just two. What was that formula?
It's R, right.
RT is equal to?
Product over the sum. R1 times R2 divided by R1 plus R2.
So product over sum. So we could substitute this and turn this into an AC formula. Instead of RT, what do we call RT? We no longer have RT. We have what? ZT. So it'll be R1 times, R1 is measured in ohms. What am I multiplying that times? XL divided by, be careful with this now. Have we been dealing with the sum? What have we been dealing with? What did I call that? the vectoral sum. So this will be the product over the vectoral sum, x sub L squared, square root of R1 plus x sub L squared. The product over vectoral sum. This is another way that you could solve that ZT. And you already know how to do it. Because in DC, you all remember this formula, product over sum, right? So no longer are we dealing with the product over sum. We're dealing with the product over sum, but we have to now deal with the product over the vectoral sum. So if you really want to have fun with Z, calculate it out this way. And if you don't do it this quarter, that's fine. We'll get to you when you get to third quarter, and we'll have you do the formula in third quarter. Either way, before you graduate, we're going to have you do this formula. Might as well use it now. It's another tool in your box. Make sense? Here's a parallel circuit with a resistor and a capacitor. Same thing. Voltage is going to be constant. I've got current flowing through the resistor. I got current flowing through the, giving the appearance is flowing through the capacitor. So I have I sub R and I sub C. The impedance of a parallel RL and RC circuit is smaller than both the individual resistance or reactance, right? Because we know that ZT has to be less than the value of least. Use the reciprocal values of Rx and Z. I don't recommend you do this. You can try it. Just a lot of moving parts. Mathematically it will work, but all trigonometric functions previously mentioned are applicable. To figure inductive circuits, I is equal to square. What kind of circuit are we looking at here? What kind of a circuit is this? I square root of IR squared plus IL squared. What kind of a circuit are we looking at here? Series. Is it a series circuit or a parallel circuit? Parallel. How do we know it's a parallel circuit?
Because you're taking the reciprocal part.
What's constant in a series circuit? Saying that backwards. What's constant in a series circuit? Current. So is there going to be any vectoral sum of current in a series circuit? Yeah, so this is going to be what kind of a circuit? In AC, come on, help me out, guys. First thing is we talk about what kind of our voltage source. In AC, is a series or parallel? Parallel circuit that contains a resistor and an inductor. How do I know that? I'm taking the vectoral sum of the current through the inductor and the current through the resistor. Does that make sense? What kind of a circuit is this? AC, parallel, RC circuit. How do I know that? Because I'm taking the vectoral sum of the current through the resistor and the current through the capacitor. If this were a series circuit, they're the same. Current's constant in a series circuit. Make sense? To determine the power consumption of a purely resistive AC circuit, obtain the average power, calculate the product of the RMS current and RMS voltage. It's average power. Voltage times current, it's average power. Power factor, the ratio of true power in watts to apparent power in voltamps. True power is measured in watts because true power is the only power that's actually being consumed in the purely resistive element of the circuit. Is the reactive element of the circuit consuming any power? No. Okay. Now, remember how this chapter is titled Resonance? We haven't even talked about resonance yet. Now we're going to talk about resonance. Resonance, a resonant device produces a broadening and dampening effect. Resonant circuits pass desired frequencies and reject others. An example would be a television tuning circuit. An example of resonance is plucking a guitar string. When you pluck a guitar string, it vibrates at a unique frequency. It is resonating. If you get a piece of china and you ding ding the china, the frequency it resonates at, ironically, is called its resonant frequency. The biggest example of a man-made device resonating took place here in Washington State. The Narrows Bridge. The wind blew across the original Narrows Bridge. We're, I think, on version number 3.0 right now. The original Tacoma Narrows Bridge, the wind was blowing and it began to resonate at its unique frequency, which meant basically it would break itself apart. That was mechanical resonance. In electronics, resonance is when, take notes on this, in electronic, resonance is when X sub L equals X sub C in a circuit. Another XY plot. Okay? This is X. This is actually amplitude, reactance, and this is actually my x-axis is frequency. Okay? When I have X sub L equals 2 pi FL, when I'm at a low frequency, my X sub L is going to be at that looks like a C. Low. So at a low frequency, X sub L is low. At a high frequency, X sub L is high. At a medium frequency, it's medium. Make sense? X sub C is equal to 1 over 2 pi FC. Do you agree with that? So when I'm at a low frequency, my X sub C is going to be high. When I'm at a high frequency, my X sub C is going to be low. When I'm at a medium frequency, it's going to be medium. So when I plot these out, this is X sub L, and this is X sub C. This is what I'm going to get. Because at low frequencies, X sub C is high. At high frequencies, X sub C is low, and the opposite is with the inductor. So when I combine both of these circuits, both an inductor and a capacitor in a circuit together, and I apply the frequency that hits this sweet spot right here, the point at which X sub C equals X sub L, this point right here is called resonance. How much phase shift does capacitive reactance give me? Pure capacitive reactance, how much does it give me? 90. How much does pure inductive reactance give me? 90, in the opposite direction. How many degrees of phase shift is there now between the capacitive reactance and the inductive reactance?
180.
180. And they're both now at the exact same value, so what are they doing? Canceling each other out. What's the only property that you're left with in the circuit? If X sub L cancels X sub C out, what's the only property we have to deal with that's left? It's the first thing you learned about here. Resistance. At resonance, X sub C cancels X sub L out, and the only thing you're left with is resistance. That's a good thing. That makes it easy. Because remember, like several chapters ago, it was a resistive AC circuit. That was easy, wasn't it? I thought it was easy. So it occurs when the circuit's inductive and capacitive reactance are balanced or equal. We use this inside tuning circuits, inside televisions, inside radios. In a resonant circuit, both the inductive and capacitive components are at the same frequency, the frequency of resonance. Reactances are equal but opposite, used with radio frequencies and tuning receivers and transmitters. These are not used in audio bands of frequencies, because in audio we're specifically talking about what? What type of resonance? Acoustic resonance. And acoustic resonance, believe it or not, this room, this space, has an acoustic resonance to it. And if you find that sweet spot and you put your speakers in just the right location, pow, music is going to pop, things are going to happen. That's acoustic resonance. Here we're talking about electromagnetic resonance of a signal. In summary, Ohm's law applies to AC circuits the same way as it does DC circuits. The AC current lags the voltage by 90 degrees in the inductor. The AC current leads the voltage by 90 degrees in a capacitor. We use vector representation to depict this. Through vector representation, we could determine impedance, apparent power, power factor, and ultimately identify a resonant frequency. Resonant frequency is where X sub C equals X sub L. And they cancel each other out. Anybody have any questions on anything we discussed in this chapter? There's a lot going on in this chapter, but really this chapter is nothing more than X sub L equals 2 pi FL, X sub C equals 1 over 2 pi FC. When they're equal to each other, you're at resonance. Check this out. Check this out. If I'm below resonant frequency, if I have a circuit, a series circuit that contains a resistor, an inductor, and a capacitor, and I am below resonant frequency, what kind of a circuit am I dealing with? You're looking at the answer. If I'm below resonant frequency, what kind of a circuit am I dealing with predominantly? Capacitive circuit. If I'm above resonant frequency, what's the predominant value that I'm going to be dealing with? Inductive. The blue cancels out the red, the blue wins. If I'm above resonant frequency. If I'm below resonant frequency, the capacitor wins. So you're either going to be dealing with an X sub C circuit, an X sub L circuit, or a purely R circuit at resonance. Make sense? Don't expect you to all be experts on this chapter. I mean, we want you to be familiar with phase shift. We want you to understand the trigonometric functions that are taking place here. And obviously, we expect you to be able to solve some of these basic problems. But I think you guys did that for me. I saw you do it in the simple series circuit that I had. Calculating out angle theta, calculating out the length of my hypotenuse. Kind of funny, you guys all calculated out the length of my hypotenuse tonight. It's pretty entertaining. And you got it right. Any questions on this chapter? Okay, we're going to do a brief 7-minute break. Okay, because then we come back, we're going to do chapter 18. Other than that, we're going to have to defer.